keep in mind that we would like to hear from you what the topic of your paper will be for the assignment as discussed in the first class. I mean, are there any questions related to this assignment? It's for everybody clear that the students that are basically in their second master, that they're working on their master thesis, that the topic can be related to the content of the master thesis, but we need to receive a title and an indication on whether or not you're on whether or not you're a master thesis student and the topic is related to your thesis, or if you decided to select a different topic. But I started early, so don't worry, because I had just this slide on the board. The most important thing I wanted to point out was the fact that we were expecting a topic title and an outline for the paper assignment for the exam. Has everybody found a time slot to register for the exams? Because there were also, I understood that the time slots on the Friday session were all booked, so they opened a new session on Tuesday. That's fine. I mean, either during the break or at the end. So if people have, everybody found the time slot except for the one person that has some questions. I realize it's a little inconvenient that 1/3 of the group will have to come on Tuesday, but there were, I mean, some conflicts on Monday for apparently some of you that did not work out to come up with the Monday time slot. I proposed a Thursday time slot as well, but the exams officially only start on Friday, so that complicated that aspect as well. So everybody's fine with this? Then we can move on to the content of today's class, and I will be talking about surface preparation, not so much about characterization, and just a little bit on thin film deposition technology as an introduction to the classes that will come, but also as a bridge between the surface preparation part and the deposition processes, because there's a key connection between those. I basically labeled it with an IC twist, because many of the examples will obviously come again from the domain of silicon technology, but are not restricted to that domain only. So I try to put the aspects as general as possible. So the outline is, I will talk about the three key concepts for surface preparation. So basically controlling the chemical surface condition, removing contamination that is present on the surface, and preparing the surface for the next process step. And the next process step after a cleaning or a treatment step is very often a surface coating process. Now there is one surface coating process that I will describe in a little bit more detail today, is the oxidation process, and the other deposition processes will be dealt with in the subsequent classes. And then as the last 2 slides of the session, I will just show an overview of some typical surface characterization techniques, of which a number of them were addressed in the last 2 classes, but I will also link them to the application domain a bit more. So I said, I mean, for the surface preparation, and it seems the beamer is a little off from the screen, but I think most of it will be readable. So from the cleaning point of view or surface preparation point of view, there is 3 key domains where we have to consider cleaning. Now, cleaning is a chemical treatment, and in most cases a wet chemical treatment of the surface with the intent to achieve one of these 3 goals here. And what do we mean with controlling the chemical surface condition? Well, this is where a small problem appears. I don't know if it is possible to align it. Do it like this. I can show the slides like this if that helps you. So the chemical surface conditioning that we would like to achieve in many cases is, and I took here the example of a silicon surface. So you have a silicon surface here at the bottom. So it's a crystalline structure of tetrahedrally coordinated silicon atoms, which can either be in a situation like you see on the left-hand side, and in that case the surface is hydrogen terminated, as we would say. So that means that all of the end bonds on the surface are protected by hydrogen. The other type of passivation is shown on the right-hand side, and in this case you basically see that there is an intersection of oxygen between the silicon atoms on the surface. Now the amount of oxygen intercalated in that surface can vary, and that's basically what we will achieve with an oxidation process. So we will control the thickness of that oxide layer by an oxidation process. But that is not what I'm trying to point out here at this point, and my battery is running low as well. It is basically the OH termination that you see on the top layer here. So in this case, the silicon atoms are terminated by a hydroxyl group. Now this has important consequences in terms of these surfaces. Now let's first talk about some definitions. So we call this a hydrogenated surface. We'll call this a hydroxylated surface. The behavior of such a surface is that it is hydrophobic in nature. That means if we put a droplet of liquid on the surface, it will basically de-wet the surface, and you will have a very large contact angle. That is typical for a hydrophobic surface. If we have a hydrophilic surface, like in the case of the OH termination, this will like water, so a droplet of water put on the film will spread on the surface and will nicely wet the whole surface. That is usually reflected by a very small contact angle, so close to or below 5 degrees. In this case, it can be up to 90 degrees or higher as a contact angle. Now, there's a couple of other things that are remarkable in terms of these surfaces. In the case of a silicon hydrogen terminated surface, we'll see that this surface is not stable in air or in water. So if we leave this exposed for a long period of time to ambient, where there is bountiful oxygen present, or we immerse it in water, it will basically migrate to a hydroxyl terminated surface. So this is not stable. The other thing for the hydroxylated surface is that the fact that you have these OH functionalities there means that they will behave as weak acids or bases, so that they can, dependent on the pH of the solution that is in contact with the surface, they can become protonated or deprotonate. So the surface charge of such a surface can be either positive, negative, or neutral, depending on the pH of the solution that is in contact with the surface. Now, why this introduction and why the link with contamination? Well, the behavior of contaminants or the susceptibility of such a surface to contaminants is different. In general, if you have noble metallic ions, so gold, copper, and related, there will be a pathway through redox reactions to contaminate such a surface. On the other hand, if you have ions present in the solution that can basically exchange with the protons here, then they can become absorbed on these surfaces. So here you have absorption on the OH groups. Here you will have, through a redox reaction, contamination present on the surface. On top of that, there's the risk that you have particle contamination, and particles means that these are items that are not necessarily pure metals or pure organic compounds, but that have a particle-like, a dust-like behavior, and in many cases we have to remove them. Now, the reason why we have to remove contamination, I have a couple of examples here. So the figures here on the left, this is what can happen to a surface if you have a particle present on the surface. So in the top image here, this is an electron microscopy image of the surface, and you can see there's a particle on that surface with a specific dimension. Now, in our processing, we often will go for a patterning process, so whereby we use a lithography step to describe a pattern on top of the surface, and then we'll use that pattern to transfer the image in the underlying layer through an etch process. Now imagine that the particle is present there, and we're just going to put a resist coating, and we're going to develop a process in there, and you can see that this particle is blocking the pattern that we're developing on the surface. And subsequently, if we then transfer the surface, we will have non-continuous lines here. This will lead to a failure. If this happens to be the case in the integrated circuit that you're making, then you have a non-connected line or a non-continuous line, and you will have a failure there. That is why, in terms of particles, like I said in the first class, we typically target a cleanliness of the surface equivalent of a ping pong ball on a soccer field. That is sort of the cleanliness that we would like to achieve. We can tolerate at maximum one ping pong ball on a soccer field, but then reduce to a 200 millimeter wafer dimension or a 300 millimeter wafer dimension. Another problem occurs when you have, for example, organic contamination on the surface. This particular case, we have an organic residue on the surface, and we'll take it through a reducing environment such that ultimately, it can convert to a silicon carbide residue on the surface. So reacting with the silicon and giving a silicon carbide image. Now, in order to understand what is happening here, we also have to look at this image here. So this is a cross-section TEM of a silicon substrate on which we have an oxidation process. So we basically inserted oxygens in the silicon matrix, and we would like to achieve a very uniform, thin, in the order of a few nanometer thin oxide layer as a passivation on that surface. What you see here on top is again a silicon that is being deposited, but here it's a crystalline, single crystal structure. Here you can see there's different crystals, so this is a polysilicon layer. But that is not the important part that I would like to describe here. Basically, the oxidation is a uniform conversion of this layer, so that you have one 2 nanometer uniform coating on the silicon wafer. If there's now a particle of this nature, you can see what is happening here. Again, here we have our crystalline surface here, and basically the oxidation process is inserting oxygens in between the silicon layer. So we're converting this crystalline silicon into an amorphous structure like we see here. And if there's a particle here, the oxidizing species are basically blocked from oxidizing the area underneath, and we have the silicon crystal still penetrating in that oxide layer. So if this is an insulating layer and we have a spike of silicon underneath that particle because we could not oxidize underneath, then we have a problem because we will have an electrical failure in that transistor that we make on that area. So you can see contamination can either block a pattern, or it can block oxidation processes and therefore be a risk. There's also a risk associated with the third category of contamination. So we have the particle type residues, we have the organic residues, and then we have metallic contamination. And metallic contamination will also have an effect on the performance, which is more difficult to describe, but you can have ionic charges in that oxide, you can have doping of the substrate. So there are a variety of problems that relate to the metallic contamination. What you need to remember at this point is that there's three types of contamination that we have to deal with. So we have particles, the organic contamination, and metallic contamination. So again, taking a graphical representation of a surface, this would be our surface with all of the various species that could be present on that surface. We have, like I said, if we expose the surface to an ambient, it will oxidize. So it will basically form a passivating thin oxide on top. We may have organic impurities, absorbed molecules on top of the surface. We may have metallic contamination on the surface, and we may have particulates on the surface. Things with dimensions larger than just an atom size or an ion size for the metals, or a molecular size for the organic impurities, but in the order of several tens of nanometers, which can be present on the surface. Now, the purpose of cleaning is to remove whatever impurities are on the surface related to the previous step and preparing it for the next step. And in order to do that, we often use wet chemistry. So we will bring the surface in contact with aqueous solutions, either acidic or basic, and very often also with an oxidizing component in there. So cleaning, you could say, is washing the dishes. So you use a wet chemistry to remove the dirt from the plates. That is what you're doing here. And instead of using a soap like you would use in typical wet cleaning, in our cases, we use oxidizing or reducing chemistries, and we will use aqueous or solvent-based chemistries. Now today I will mostly concentrate on aqueous oxidizing solutions, aqueous reducing chemistries. I will not specifically touch on the solvent-based chemistries. Now, cleaning is a little bit of a complicated term because cleaning can also be the source of contamination. If I have, again going to my dishwashing, if I have clean solution and dirty plates, then I will basically remove the contamination from the dirty plate going into the dishwashing solution. But if I would have dirty dishwashing water, I mean, I've been using this for 500 plates, and I put a clean plate inside that solution, then the risk is that the contamination from the liquid will basically go back to the surface. So it's always an equilibrium between the concentration that you have in the liquid and the concentration of the compounds that you have on the surface. That's what I described here. A dirty surface plus a clean chemistry there's a possible removal of the contaminants. On the other hand, if you have a clean surface and a dirty chemistry, there's a risk that you basically recontaminate the surface, and that all of the effort is useless. Now, this is, in another way, the dishwashing process described. If we do, take again, look at the image here below. This is our surface of the silicon wafer. And anything above, up to the dashed line and above, is the cleaning solution that we bring in contact with our liquid. What is happening? Assume we have chemical contamination on the surface. It can be chemically bonded, it can be physically absorbed, but the chemical contamination is on the surface. So in order to achieve cleaning, the first thing we have to do is to overcome the forces that keep the contamination on the surface. These can be van der Waals forces, these can be chemical bonds, but we have to overcome the interaction of the contamination with the surface. Well, that is that middle term, potential energy. We have to use a source of energy to release the contamination from the surface. What needs to happen next? Well, the contaminants will have to diffuse away from the surface. That's the removal process. They will go to the bulk of the liquid that you bring in contact with them. That is the first term, the concentration gradient. So we have indeed a concentration gradient taking the contamination away from the surface to the bulk of the liquid. This is also where the previous slide comes into play, because if the concentration in the bulk is higher than the concentration in that boundary layer, we'll have the reverse process, and contaminants will basically diffuse to the surface, and then they can be exposed to adhesion forces, and they will recontaminate the surface. So that's the equilibrium that is happening. And once the contamination is in the bulk of the liquid, it is basically removed from the substrate. This is what you would do in the rinsing step in your dishwashing process. So you rotate the wafer in, or the plate in the dishwashing solution, and then you rinse it. So you remove the boundary layer, you remove the contamination. So all this to basically say that a cleaning concept is an equilibrium of these three steps, and we have to make sure that we overcome the adhesion forces. We have to make sure that we have a diffusion process over a boundary layer, so over that exchange layer, and that we then have a process to remove the contaminants from the bulk of the solution. So you have an interaction at the surface that has to be overcome, and a transport away from the surface, first over that boundary layer, and then by a flow, a convection process in the bulk of the solution. So basically I could stop here, because that's all you need to know about cleaning, the combination of these three steps. But I'd like to make it a little bit more visible in terms of what it means for a number of the contaminants that we discussed before. So if I have a particle on the surface, left image, the particle is attached to the wafer surface. In many cases we can assume that it is held there by van der Waals forces. So forces that will play on the short range, that are always attractive, and they will depend of course on the medium and the material. But the particle is held there in place. The first thing we have to do is break these van der Waals forces. And in the cleaning step, this will be done in some cases by just under-etching the particle. So by removing a few layers of the material underneath the particle, such that the contact area between the particle and the surface becomes less. And the van der Waals forces, the attractive forces, are weakened. And then we'll have a lift-off process, and this is where we'll play with the chemical surface conditioning. If we can make sure that the surface charge on the wafer and the surface charge on the particle is such that we have a repulsive force, then we'll just push away the particle even more. So it's again a combination of the repulsive character and the under-etching. Under-etching is one way. We can also use mechatronics, which is a sort of agitation, so we would have the particle and the wafer vibrate at different frequencies, such that the particle would momentarily become loose from the surface and it can be lifted off. But in general, we have to overcome the van der Waals attractive forces in such a way that the repulsive forces can take over, which we can control by the chemistry. Again, the opposite process is true as well. If the particle approaches too close to the surface, the van der Waals adhesion can take over and we recontaminate the surface. So, to make that, well, not necessarily more clear, but to make it tangible, I have here a plot that is in there for just for exploratory purposes, not to know this plot by heart specifically, but you can see what we have plotted on the y-axis is the particle removal efficiency. So we have a surface contaminated with 100 particles, we do a treatment, and we measure after the treatment how many particles are remaining, and that is expressed as a percentage removal efficiency. So 100%, or 1 in this case, means that we cleaned all of the measurable particles from the surface. A cleaning efficiency of 0 means we did not do any cleaning at all. And then what we have on the x-axis is the equivalent edge depth, so the surface that the amount of material that we removed from the 0 level to a level. So we removed between 0 and 15 nanometers equivalent of a surface. So we're in the situation, the middle situation, where we're etching back the surface underneath the particles, visually. The different colors that you see here are different types of particles on different types of surfaces. That's all you need to know. We have a nitride particle, an oxide particle, an aluminum particle on bare silicon, on an oxidized silicon, and on another type of oxidized silicon. But just look at the shape of the curve. So we have very poor particle removal efficiency if our cleaning process is very short, meaning if we only remove just a little bit of the substrate. And from a roughly equivalent thickness removal of 3 nanometers, we all of a sudden have a drastic shoot up in the cleaning efficiency, meaning we go to almost 100% cleaning efficiency in this particular case. So this is a demonstration that this process is working. I think, the next slide is just a little bit more mathematics, not to be known, but this is more for reference. So the van der Waals forces basically are proportional to the radius of the particle. The larger the particle, the higher the van der Waals adhesion will be, and they're inversely proportional to the distance between the particle and the substrate, so the Z factor. That means they will work indeed at short range, and they're always attractive. The electrostatic interaction is a more complex expression, but you see there's 2 terms. The middle 2 terms in the index below that describe the surface potential of the surface and the surface potential of the particle. By controlling the surface potential, by controlling the charges, we can generate repulsive forces. And they are proportional to the distance between the particle and the surface. So the longer the distance, the higher the electrostatic forces will be. So the higher attractive force will play because they will be attracted by a charge towards the surface. And then you have solvatation forces as well that shield to some extent the charge on the particles additionally. And then there's also a factor, the Debye-Huckel inverse double layer thickness, which I described here. So if a particle has a charge, you will have the opposite charge assimilated around that, and then you have a double layer with again the same charge as the particle. This is typically how a charged particle would be present in solution. The only point to remember here is with respect to this Debye-Huckel length, there's a factor, the ionicity or the ionic strength of a solution. And you can see that by adding acids to the solution, we can change the ionicity of the solution, and we can influence the Debye-Huckel constant, and with that we can also influence the behavior that the particle has with respect to the surface. So again, I'm just trying to give you the larger perspectives of cleaning. Moving to the next contaminant that we can have in solution, and it is metal contamination. Metal contamination in aqueous media is best described by what is known as a Courbet diagram. Now, a Courbet diagram is for a certain species, so calcium in this case, describing the presence of that species as a function of the pH and as a function of the potential of the solution, so the PE. And depending on the pH of the solution and depending on the oxidizing power of a solution, a species will be present in a different chemical format. They can be present, in the case of calcium, as a doubly charged ion, but they can also be present at high pH as a hydroxylated species. Or at high oxidizing power, they can basically be present as calcium oxide particles. So, but with this, you can already see that by playing with the pH and by playing with the oxidizing power, we do have tools available to control how ionic metallic contamination behaves in solution. What is important to know is that for metallic contamination, as a rule of thumb, you will have good solubility at low pH. So there's a tendency for metallic contamination to be removed from the surface if you work at low pH. There's a high risk of forming hydroxide species, insoluble species which will absorb on the surface. So for metallic contamination, moving away from high pH is beneficial. Remaining at low pH, remaining at low pH is beneficial. Working at high pH is detrimental. High pH, there is a high risk that metallic species will go on the surface. I forgot to mention one thing, that for the particle removal, the opposite is true. So for particle removal, the etching of a surface happens better at high pH. So if you have high pH, you will have more surface etching. And you already see the contradiction here. For a particle removal, we prefer high pH. For metal contamination, we prefer low pH. So there's the constant debate or the constant dilemma on how to work with the cleaning solutions. And there's no tailored solution that will solve all the problems. You will have to design it based on the process under consideration. Now, there's one thing that I did not specify is the oxidation potential of a solution. By adding oxidizing or reducing components to the cleaning solution, we may also have a plating, so a redox couple being formed, and the risk that contamination basically, instead of absorbing on the surface, plates on the surface, so that it forms a metallic residue on the surface. And that is one thing that we need to take into consideration as well. One is that reducing activity or the metal plating becoming a concern. Well, it becomes a concern when we have a hydrogenated surface. So going back to one of the first slides, a silicon surface that is hydrogen terminated is very likely to undergo a reduction reaction of metallic ions in solution because of the fact that the silicon can become oxidized. So the silicon becomes oxidized and the metal ions, the ones that are more noble than silicon, will become reduced. And we will introduce copper metallic contamination on the surface. So we'll have to reverse that process using an oxidizing chemistry to remove the particles, the metal contamination from the surface again. This type of process here is extremely riskful when we work with a hydrofluoric acid solution. Anybody an idea on why that would be the case?
Fluorine has a high affinity for silicon.
It has high affinity. HF actually will dissolve the oxide, so it etches the oxide. Now, if it etches the oxide, then you basically keep the engine running because you can again oxidize the silicon, plate the metal, and then the oxide is etched again. So in HF solutions, you will not only have a hydrogenated surface, but you will maintain a hydrogenated surface because of the fact that the HF is etching the oxide and the noble metals can plate out. The non-noble metals are not a concern in this particular case. But keep in mind, metallic contamination on an oxide-free surface, be aware when you have to deal with noble metals. Is a hydrogenated, a hydroxylated surface, so a surface where we have OH groups, is that fine? Unfortunately not. In order to explain this, we just have to go back to the fact that an OH terminated surface, the OH groups are behaving as weak acids. So basically, we can write this equation here, so that the OH terminated surface can lose a proton and can form a dehydroxylated charged surface site. On this surface site, a metal ion can absorb, and the metal ion basically becomes chemisorbed on the surface through an SiO-M type of bond. That's, I hope, obvious from these two equations. Now, the total amount of surface sites on a surface of a silicon wafer, they're either either protonated or they have a metal ion absorbed on that. And then depending on the pH, you also may have some deprotonated surface sites. But the total amount of surface sites is limited, and it's in the order of 10 to the 13th surface sites that you would have available on a surface. So that means that you can theoretically absorb up to 10 to the 13th atoms of metal ionic species on these hydroxylated surfaces through that exchange reaction. Now you can rewrite the equation here, and then you basically come up with the conclusion that the number of sites that are occupied by metal ion are proportional to the total amount of surface sites, logically, and are inversely proportional to the pH, and, well, most important, inversely proportional to the pH. So we can already see that if we have a high acidic solution, we have high proton concentration, and we will have very low metal contamination on the surface. And that is what you see expressed in this graph here. So you have the calcium 2 plus concentration in solution, and we have the surface concentration of calcium measured on a wafer. And you can see that there's a drastic drop-off, obviously, with the metal concentration, but there's also a strong dependency on the pH. At low pH, we have less surface size than at high pH. So again, I mean, this is where low pH is beneficial. And this slide is comparable to the slide that I showed on the particle removal. You have the chromium concentration in this case on a wafer, and as a function of the removed oxide layer. So also here, etching will also help you in reducing the surface concentration apart from the pH effect. Now, there's some points here in this corner here, and in this case we talk about chelating agents. So one trick that is often done when we're working at high pH solutions, which is in this case happening, we would have at high pH theoretically a lot of surface sites occupied by a metal ion. But if we can take the metal ions that are in solution, if we can sort of neutralize them by forming a chelate complex, so by basically having them interact with EDTA, for example, then they are not part of the equation anymore, and they will not contaminate the surface. So you can also play on the chemistry side. Once they are released from the surface, then you can basically complex the metallic ions and keep them in solution. So basically play with the diffusion and the removal process, the two other terms in the cleaning equation that I showed earlier. I have an example on that, but it's just a little further in the notes. And then the last part is organic contamination. Well, the first thing to know is that organic contamination basically comes mostly from airborne absorption. So if you expose a wafer or a substrate to the ambient, organic contamination can basically adhere to the surface. Now, I showed you in the first class that we work in clean room environment, and when you talk about clean, you think, well, great, I'm fine in terms of the ambient, and there's no risk of contamination. Well, for organic contamination, it's slightly counterintuitive that if you would store a surface, say here, or you would store the same surface in a clean room environment, you'll see the top part, the peaks are indicative of organic contamination. The bottom part is in the clean room, and you have more peaks and higher intensity. So my clean room is not that clean as you would think. Anybody an idea on why that is the case? Yeah.
Because molecules, they migrate to the particles, and a lot of particles can.
That will also play a role. I mean, but it's mostly because of a clean room is made up of organic or plastic materials. So there's a lot of plasticizers. There's a lot of, I mean, degassing of the materials from the clean room possible. So the ambient, the concentration in the ambient of organic compounds in a clean room is higher than you would have here in a classroom. We'll have tons of more particles here in this clean room, in this area than in the clean room, but in terms of concentration of the organic compounds, because of the atmosphere is higher. If you have a higher bulk concentration, you'll also have the reverse effect, so more diffusion to the surface and a higher risk of contamination. So that's what I wanted to say there. Where are they coming from? Well, they are coming from phthalates, esters, siloxanes, which are used from the wall material, which are used from the sealants, which were coming from from the HEPA filter. So the HEPA filter is a filter that is used to remove particles before they go into before the air goes into the clean room, but also from some of the processes that we run in clean room environments. We use photoresist materials, which are organic materials with solvents. So there's just a higher background concentration explaining the effect. Organic contamination will absorb on both types of surfaces. Here you see if you have oxygen or other type of moieties in your organic molecule, then they would obviously be more susceptible to surfaces that are hydroxylated. So the OH groups would then form sort of water bridges, and that explains on how the organics are held. Similarly, if you have molecules with less of those oxygen moieties, they would also tend to absorb more on the hydrogenated, so the hydrophobic surfaces. So both the oxide and the non-oxide silicon surface are prone to organic contamination. This is a slide to explain how we would remove organic contamination. Organics, so they can be oxidized. So obviously, if we use an oxidizing process, we will be able to remove organic contamination. And what I'm saying here is a process whereby we use ozone, so ozone as a gas, dissolved in liquid to achieve the cleaning potential. Now we can use ozone in two ways. We can either dissolve the ozone in the DI water and then spray the wafer with ozonated DI water, or we can have a process whereby we have a very, very thin water layer on the surface, which is the right-hand side, and we bring it in contact with ozone gas. Now, the right-hand side process is more efficient than the left-hand side process. And why is that? Well, again, the diffusion process plays a role. We need to have our organics are the red line on the surface of the silicon. Now, ozone is very poorly dissolved in water. We typically would have milligrams per liter of ozone dissolved in the eye water. So we have a very small quantity of cleaning substances available in the bulk of our liquid, which have to diffuse all the way to the surface to oxidize and to do the cleaning steps, to overcome the chemical bonding of the organic molecules with the surface. Obviously, that is a process that works, but with low efficiency. In the boundary control process, we have a thin layer of water on the surface, but we can bring it in contact with percentage concentrations of ozone. So far more oxidizing species, which will only have to diffuse to a very thin layer of water to do the cleanup, to do the oxidizing process. So this to indicate that not only in terms of the amount of contaminants and the cleanliness of the solution, but also the amount of, or the concentration of the active species that we have available to do the cleaning, that also plays a crucial role in the cleaning process. And this is the last slide that I would, well, it's two slides, it's the last aspect that I would like to briefly touch upon in a cleaning step. Whenever we bring our wafer in contact with the liquid, we have to dry it. I mean, it's again our dishwashing process. If it's clean, we can basically leave the dishes to dry, and then you will have stains being formed on there. Or we use a towel and we basically dry the plate, and then they look, or the glasses, and then they look shinier. That is also something we have to do with our surfaces. We also have to dry them. And for your information, there's two processes that are typically considered for drying wafers. You have the left-hand side, which is a dryer by rotating the wafers very rapidly in an ambient. That is what we call spin dry, and the spiral shown on the means that the wafers are rotating. If they rotate, you basically have the forces pushing away, or the centrifugal forces working on the liquid meniscus, and you basically thin that down to almost zero thickness. The problem, whenever you rotate something in an ambient, there's a problem that you have a suction and that you basically recontaminate the surface with particles. The Rotagoni process that is described on the right-hand side is also rotating the wafers. But in this case, we also use a tensioactive fluid to help the removal process. We rotate at a lot lower speed, and the Rotagoni is derived from the Marangoni effect. And the Marangoni effect is described in the upper right corner. So if you have a tensioactive vapor in contact with liquid, you will have a dissolution of that tensioactive vapor. Now, the concentration of tensioactive vapor or tensioactive component in the liquid meniscus here will be higher than in this thicker part of the film. So if you start rotating, we'll have a slightly higher concentration here than here. And the Marangoni effect says that the liquid will basically flow from an area with a high concentration of tensioactive component to an area with low tensioactive component. And this is what you see here. So we have the grayish part is a substrate that is wet. The purple part is a surface that is dry. And we have liquid being sprayed on the wafer, but next to that we have an injection point of a tensioactive vapor. And we gradually move this part to the outside of the wafer. So we basically move it from the center of the wafer to the outside of the wafer. And you can see we're drying the wafer from the inside out. We're really pushing the liquid off the wafer, and we end up with a clean wafer. Since we're working at lower rotational speeds, there's not so much of a risk of water contamination, particle contamination, because they will remain in that liquid layer and are removed together with the liquid from the surface. We also have less of a thin boundary layer of water remaining, so there's no risk of drying marks being formed there either. So this is the Rotagoni effect. So we basically move this nozzle out while we rotate the wafer, and like this we dry the wafer. So with that, I basically described the key aspects that play in whenever we have to deal with a cleaning step of a surface. So the cleaning is an equilibrium of 3 steps. We have to overcome the surface interaction. We need a diffusion away from the surface over the boundary layer, and we have a transport away from the substrate, the bulk of the liquid, by means of a convection process. So I have convection, diffusion, and overcoming the surface interaction. The contaminants we're typically dealing with are particles, are metallic species, and are organic contamination. And we can achieve a lot of cleaning by using aqueous solutions, either acidic or basic, with an oxidizing compound in there. And for the people that are interacting with IMEC or with the microelectronics industry, just a few more words on typical cleans that are being used, and so the oldest described cleaning sequence is an RCA clean. Now, RCA was a company that made electronics in the 70s, and besides of their cleaning concept, or the name of the cleaning concept, nobody in the room probably will remember them. They were bought by other companies, but they were the ones that first described a cleaning sequence. And they called it a standard clean 1 and a standard clean 2. Now, the standard clean 1 was an ammonium hydroxide peroxide water solution. Ammonium hydroxide, high pH, peroxide, oxidizing activity. Diluted in water, and temperature always helps to speed up any chemical process. Now, you would wonder why the high pH, whereas you have been saying, I need low pH to remove the metals. Yes, but I also said you need to have some etching. And whenever you have to clean silicon, OH minus is good in etching silicon. So it's the OH minus compound here that will give you the etching process. In recent literature, you will see this described as an APM, or an ammonium peroxide mixture. Problem, metallic contamination. So that is why they introduced the standard clean 2, hydrochloric acid peroxide water, again at 70 degrees C, and that was then the hydrochloric peroxide mixture in other terminology. Acid solution is good to remove metal ions from the surface. Here we have an oxidizing compound, so we'll have an OH terminated surface. If we have high acidity, we will have low metal contamination on the surface. All of these steps are followed by a rinsing step, because we have to get rid of the nasty chemicals, the highly concentrated chemicals here, and we have to do a drying step. There's no drying step here because they move the wafers from here wet into the rinse stage, and from the rinse stage into the acid stage, and from the acid stage into a rinse stage, and then into a drying stage. Now, over the years, people became more aware of organic contamination. So, because of the awareness of the organic contamination, they extended the cleaning sequence with piranha step, so sulfuric acid peroxide mixture. This will oxidize the organics and clean the surface from the organics. Again, it's a pretty concentrated mixture here at 90 degrees C. They call it piranha, and I think you understand. I mean, well, I hope you will never come in contact with the mixture, but sulfuric acid basically dehydrates and oxidizes. So if you put it on a cube of sugar, it will turn black, and exactly the same will happen with your skin. So exactly the same will happen with the organics that you have on the surface. The problem here is that the sulfur is a very viscous liquid. So it's very difficult to rinse it off. And the sulfur will also become incorporated in the oxide that you form on the wafer. And that leads to detrimental effects. And that is why after this step, they introduced an HF step to remove the dirty oxide from the surface, and then to go for the particle removal. Now you already see again a contradiction here, because now I have a hydrogenated surface, HF. So if I have metal contamination, noble metal contamination in solution, I'm removing the dirty oxide, but I may be introducing metallic contamination. So no clean will do it all unless it is perfectly balanced for the purpose that you would like to achieve. So, like I said, the RCA is the oldest documented clean. It was the standard clean 1, which is ammonia peroxide. It removes particles, but there's an issue with the metal contamination. Standard clean 2 is the hydrochloric acid. it removes metals, but there's an issue with the particle contamination. And later on, it was extended with the sulfuric peroxide and the hydrofluoric acid clean. Now, if you pay attention, these are pretty high concentrations of solutions. And a lot of research was done on whether or not you needed such a highly concentrated cleaning solution, whether you needed the high temperature. And probably on this aspect alone, we can spend several hours explaining this. But basically what was found was that, for example, in this solution at the high temperature, the peroxide was decomposed very quickly. So after an hour of operation, this concentration basically dropped to half the concentration. So we could easily eliminate the peroxide from the solution and still maintain the same cleaning objective. Also here, like I said, the sulfuric acid is a very viscous liquid. Its main purpose is to do an oxidation of the organics. Well, this was replaced by ozone. And also here with the ammonium hydroxide peroxide mixture, this is a basic chemistry, so high pH. If we would be able to work all acid, then we would not have a problem with the metal contamination or the reintroduction of metal contamination. So simplification of the process is a concept that IMEC worked on extensively, and instead of the sulfuric oxide peroxide, they moved to sulfuric oxide ozone, so dissolve ozone into the sulfuric acid, or even go for ozone di-water. Another extension was dilute HF. If you spike it with hydrochloric acid, you basically will complex the copper and you have less of a risk with copper plating on the solution, because you will maintain the copper as dissolved species in solution. Now here we have an oxide, here we remove the oxide, so we have an etching step. That was exactly what was needed to remove a particle. You need to remove part of the substrate underneath the particle. So this step alone turned out to be efficient enough to overcome particle contamination of the surface. You have an acid solution, so there's no risk of metal recontamination. The only thing is, in some cases, we would like to have a hydroxylated surface and not an HF terminated surface, and then we do a reoxidation of the surface, and then we do the Marangoni dry. Just as a few numbers, I mean, this was typically lasting for 60 minutes. This can be done in 33 minutes. And the amount of water that you consume is drastically less. This is for a full batch, 25 wafers in a multi-liter basin. But you can reduce the amount of water drastically. Why? You don't have to rinse highly concentrated sulfuric. You don't have to rinse highly concentrated ammonia. So you can use less water in the rinsing steps. This is another description. So this removes the organics. You have a chemical oxide growth. Here we remove the oxide, and because of removing the oxide, you basically have a particle and metal removal because it's in acid conditions. Then you have a clean chemical oxide and you keep the pH low. So there's no metal and no particle redeposition, and you can dry without drying marks with the Marangoni dry. This is a slide that I should have used earlier. This is on the complexing agents. So these are species that you can add, and they will complex with metals that are in solution and prevent them from re-adhering to the surface. And with the complexing agent added to the ammonia mixture, to the high pH mixture, you can also prevent the recontamination, or you can achieve cleaning of metal compounds in basic solutions as well. So I should have kept them earlier in the slides. Before moving to the surface coating part, I will take a 5-minute break.